Okay, so there is one question about can convexity, so last time we were talking about convexity of three different things we spoke about. Convexity of what? How do I combine points? Convex combination of points was the first thing. The second thing was set. Third thing was function, right? So the question is related to the third one. Can convexity be checked by a double derivative test? What do you think? Convexity of what? A function. So remember we drew the function, right? It was like, it looked concave, but we are calling it convex, right? If it is like this, then any convex combination of the function values, blah blah, you know what it means, right? Can it be confirmed by a double derivative test? Yes, no, don't know. Intuitively yes, because what is the double derivative capturing? When does a double derivative change sign? When the first derivative itself has some change, right? So supposing I have a hump, what will happen to the double derivative? It may undergo a change of sign. So if, so the student asking the question has got it, says f double dash x greater than equal to 0, right? So that is actually correct. If a function satisfies that the double derivative is greater than 0, it is a convex function, okay? And assuming double derivative exists, is there an equivalent case for the multivariable function? So answer is yes, in fact, and we will spend a lot of time talking about this when we go to second order methods, which are also called Newton methods. Okay, so who wants to claim this question? It's a very good question. The second derivative in the case of multivariable is called what? It's called the Hessian. We will spend a fair amount of time with the Hessian, so this will get checked in. But you're right, the second derivative does capture convexity. It's actually if and only if, so it's a strong condition. In the convex function condition B, should it hold true for any alpha, or should alpha be between 0 and 1? We said for convex combination it has to be between 0 and 1. Okay. There was, I don't have the chit with me, but there was a question that we proved the continuity and all of those things for the case of the P norm with P equal to 2. So the question was, what if we choose some other norm? So there is, let me note, just mention one condition over here. It's called the equivalence of norms. So if I define everything for one norm, if I want to translate to another norm, can I do it easily, or do I have to rework? So there is an inequality over here. So this is saying that once I get something for norm A, there is a bound with respect to the norm in terms of B, with some constant C1, C2 that can be worked out. Okay. So if you get a result for one norm, you can easily translate it for another norm. Well, not easily, but okay. Next question is, coming from a ML background, working with loss function and back propagation, we see most common technique is gradient descent. But why is that the most common technique? Is it due to a computational limitation or something else? Gradient descent ends up being the simplest algorithm you can think of, and it scales well with problem complexity. So we'll talk gradient descent. In fact, will be one of the first algorithms we talk about. So we'll get to it there. I had a couple of questions about this. What is the difference between uniformly continuous and Lipschitz continuous functions from a geometric perspective? Okay. So what I'll encourage you to do is look at the Wikipedia page for a Lipschitz function that has a geometric picture, like an animation that's going on. That's very convenient. From a geometry point of view, Lipschitz continuous function is basically saying that the derivative is bounded. If a derivative is bounded, what does it mean for the function shape? Can I say anything? If the derivative is bounded, can the function do crazy things? sharp or even need not be a discontinuity, a sharp transition is going to be disallowed, right? Supposing I have a function like this, can you say something about the magnitude of the gradient? It's some gently changing function. The gradient value will be something, but on the other hand, if I do something like this, right, it's a continuous function, it's not discontinuous. There's no cut in the function, but what will happen to the gradient value? It will suddenly shoot up, right? So the Lipschitz continuous function basically imposes certain restriction on how rapidly a function can change. Same intuition is also holds true for uniformly continuous. That's the geometry. That's as far as geometry will take us. But do look at the Wikipedia page for a Lipschitz function. In the example we took, which was root of 1 minus x square, right? We showed that the function was uniformly continuous, but it was not Lipschitz continuous, right? The question is, what about the other way? If I show a function to be Lipschitz continuous, does it imply that it is uniformly continuous? We won't prove it, but there is a theorem which says yes, every function that is Lipschitz continuous is also uniformly continuous. I should have started reading this question first, but I'll talk about this at the end of class. It's more an administrative question. Okay, these two are admin questions. How is the constant delta depending on epsilon and x and y? This is something that just different examples will give you different types of bounds on delta. I mean, if this were a course on analysis, we would spend a lot of time doing it, but we don't have that luxury. All right. There is a question, why do we call, what is the meaning of the word convex in convex combination? Why do we call it a convex combination? And honestly, I couldn't find any answer for it. This is the definition of convex combination is alpha 1 x1 plus alpha 2 x2, where alpha 1 alpha 2 belong to 0 to 1. That's what we call it, right? Okay. Okay, so we have the last module of the background summary that is left, after which we start with unconstrained optimization. And that last part is actually the most important part, which is how do we do calculus with multivariable cases. Okay, so this part of the background is probably the most relevant part. Okay, so let's talk about derivative of a function. Okay, now when you look at the actual definition of the derivative of a multivariate function, it can seem a little intimidating. So let's start with something very simple that everyone is familiar from high school, right? So how did you define the derivative of a function in high school? Limit okay, let's just call it del y tends to 0. Next, f of, let's say, x plus y minus f of x divided by y, right? Will this limit always exist? No. If the function is differentiable, then it exists, and when it exists, we give this limit a special name. We call it the derivative, right? Now let me rewrite the same expression, which was very intuitive, in a slightly different way. So I can say that I didn't do anything fancy. I just combined it all on one side, right? And what do I say now in formal language? I'll say if there exists a quantity f dash x such that this is satisfied, we say that the function is differentiable and it has a derivative f dash x. Sounds much more complicated, but the idea is just basically this, take this limit, right? So this is what we did in the case of high school. Any doubts about this? I just did a rearrangement. I brought stuff on one side. That's all I did. Okay. Minus. Sorry, correct. Absolutely. Okay. So is everyone really clear about this? Here, what was here in both of these things? I said x was x and y belongs to real, right? Now let's go to Rn, okay? And what we're going to do is we're just going to use our this intuition over here, okay, and talk about derivatives, okay? Now, in the case of n-dimensional calculus, we don't write f dash x. There is another special symbol reserved for it, which is the del symbol, if you have all seen it, right? So, we write the derivative like this, grad f. And grad f simply means what? It's a column vector of what should be inside it? Partial derivatives, right? So, this is going to be df by dx1, df by dx2 up to df by dxn. Common convention is to write it as a column vector of size n cross 1, right? This is going to be size n cross 1. Although you will sometimes in some books and papers you will find it written as a row vector as well, right? Doesn't really matter. It's a collection of n numbers. Okay, so now if you were in charge of definitions and you wanted to define a gradient for a multivariable function, how would you define it? So let's say define, not dof, So let's look at our intuition is from this guy. How will I define it? Let's go term by term. Should I retain? So I'm going to put limit. Okay. Something has to go to 0. We'll see what that something is. Okay. Some relative of y. Now can I put y tending to 0 or should I? Okay, we'll come to it. So what should the first term be? Can I write f of x plus y? Right? Let's start with it. Let's not overcomplicate it. Let's just go with it, right? So f of x plus y. And just for simplicity, let me note that f is a function from Rn to R. Okay. So f is a scalar, a single number. So first term is fine. Next term, minus f of x. So far so good. Okay. Now this f dash x, right? What do I write for f dash x? I have given you the definition. I'm going to just replace it by, no, this guy, right? Grad f. Grad f is the new guy who is going to be the replacement for f dash x, right? So I am going to write it over here. Now grad f is of what length? N cross 1. Can I multiply it by y? Is that a legal multiplication? No. To make it legal, and remember this product has to be what? Has to be a scalar. How do I get a scalar out of two n length vectors? One of them I need to transpose, right? So I'm going to do this. Okay. What about the denominator? Can I write y? That makes no sense because the numerator is a scalar. What does it mean to divide by a vector? It doesn't mean anything. So what is the nearest thing you could do? Think of the intuition behind limit. I heard the correct norm, right? Now what should the limit be? Norm y tends to 0, right? So if you were in charge of definitions, you would have correctly defined the gradient of a function. It simply follows from your high school single variable case, which is generalizing to the case of vectors where needed. And the intuition of a derivative is the same, that take the difference between f of x plus y and f of x and make that deviation to be as small as possible. But now deviation, I cannot say y tends to 0, I have to say norm y tends to 0. That means a small distance, right? And whatever is left between f of x plus y and f of x is bunched into the gradient, okay? So you can see, right, if I had given you this definition at the starting of the class, it would have looked like, how did this come, right? But you see, it's quite straightforward how it came. Okay. Yeah, question. Okay, question is, why not take Rn to Rm, for example? Is that a question? Okay. Answer is quite simple actually. You start learning a cycle first and then you learn to drive a car, right? So we are starting with Rn to R. Once we are comfortable with that, we will go to Rn to Rm. There's no problem. Okay. It's easier to learn the nuts and bolts first with a scalar valued function, and very soon we'll go to a multivariable function. Oh, right. When this is equal to 0, we say that, so if grad f exists such that the above holds, then grad f is called the, there's in fact a name of, if you were born a few hundred years ago, it would have been named after you, but unfortunately, tough luck. It's called the Frechet derivative. Okay. Now, sometimes you will find when you read textbooks and papers, instead of finding grad f, you may find a symbol that goes like this. There's a subscript below the grad. What do you think that means? It means the derivative with respect to only some subset of the variables. Okay. If this is omitted, then it means all the derivatives. So that's just something to keep in mind. The concept is the same. Okay. Okay. So this was the main definition over here, right? Some more definitions you can write down like this. So if this gradient exists for all x in the domain, we call the function to be differentiable. Okay, so it's important all x belonging to the domain of f. It's not enough that you just say at some point. It should happen at all points. Then you call the function to be differentiable. Okay. Further, if grad f, now that grad f has been defined, if it is continuous, right, that's a further restriction. It need not be continuous. Okay, but if grad f is a continuous function, then f is called continuously differentiable. Just some definitions. Okay, so in fact, we get to answer the question asked just a few minutes ago. Now let's consider Rn to Rm. Okay, now it's very easy for me to just write it mathematically, Rn to Rm. But let's get a grasp of what this means before we start doing complicated math on it. So you all remember from the introductory lecture on optimization, what would be the meaning of when I say f of Rn to R over here? This is that I have a function of many variables which is giving me a single scalar output, right? So for example, in the case of an Amazon delivery person who's making several deliveries, that single function which the delivery guy wants to optimize could be, for example, one thing only, which is time. I want to minimize the time, and all the xi's are what? various inputs, fuel cost, whatever, right? How much tiffin he has got, various things can go in over there, right? That goes into this thing. Now, when I say Rn to Rm, and M could be, for example, 2, 3, whatever, what would that mean? In simple analogy, it would mean that I have several things I want to optimize. I want to minimize the time. I want to minimize the fuel. I want to minimize my exertion, supposing, right? So then I would have constructed an objective function which has, or a function which has multiple sort of dimensions, and I want to optimize along all of them, right? Which is, now you are making the model, the complexity more and more realistic. Another, a little bit more, an example closer to engineering. Let us say I'm designing an antenna. Now, an antenna, I want to make sure that it has a beam pointing in a particular direction. That's one objective. I want to have the polarization in a certain way. Okay. I want to have the bandwidth to be so much. Right. So a practical engineering problem will have so many things that I'm trying to optimize. So those many things are sitting here in the M over here. So it's not just to give you more pain in math by making M greater than 1. It's to capture real life problems over here. Okay. And as you start making M larger and larger, life becomes more and more difficult, because it's not easy to satisfy multiple objectives at the same time. Okay. It's very challenging. But we'll go through at least the machinery. Okay. Now, when we start with this F, which is now a function, an output which has, let's say, M functions over here, how, if you were again in charge of definitions and you needed to define grad F, can it still be a column vector? So if you were in charge of definitions, how would you define it? Do it for each sub function. So you have F1 up to Fm, and I have partial derivatives with respect to each of these variables, right? In fact, most likely in your first year engineering courses, you would have seen this object. What is it called? It's called the Jacobian. There's a little bit of a funny change of convention over here. When I had one function, that is just F1, my grad F was a column vector. Now, it turns out that when I go to M output variables, you would think that you would have M column vectors, but the convention is, instead of putting them as column vectors, you put them as row vectors. That's how it is. And you will find books with the other convention also. So there's nothing sacred about it. So we will assume the convention of row vectors. Okay, so it's going to be like this. So df1 by dx1, df1 by dx2, all the way up to df1 by dxn. This is the first row, up to dfm by dx. So what is the size of this matrix? M rows, n columns. Right? It's called the Jacobian. So J, if I write down the columns, in shorthand notation, this is going to be, what are the subscripts that I should put over here? The ith row will have F, I or J? I. And the jth column will have xj. Right? So this is the compact shorthand notation for the Jacobian. I don't have to always write this big thing. Okay. And I've already told you the notation for this matrix. We say J belongs to R M cross N. Right. Okay. So now that this Jacobian is out, let's continue further. So we're going to take a few of the nuts and bolts that you have studied in high school calculus and upgrade them to multivariable case. So chain rule is another thing, right? Supposing I have x is a function of t. Let's start with simple case, okay? And y is a function of x, right? And I want dy by dt. What do I do? Right, so I will write d of dt of y of x of t, and I would simply write that as dy by dx dx by dt. And that's how we do it. This is scalar case. Now, supposing I have x belongs to Rn. Okay. Now, let's say my function h of t, okay, instead of y, I'm going to call it h of t, is f of x of t. Okay. So, what this means is that each of the xi's is a function of t. Okay. And now I want grad h t. So, how would I generalize this simple definition that I had? You don't have just one x anymore, you have x1, x2 up to xn. So, how would you generalize this chain rule? So, f depends on x1, x2, all of these guys, right? So, how would I generalize it? I would take the derivative one at a time, right? So, I could do, for example, df by what? dx1 by dt, but that doesn't capture the entire flavor for f. What else is there in it? Correct. So, there's going to be df by dx2 by dt. Okay. And often this is a little cumbersome to write like this, so we can write it in shorthand notation. So, this looks like, does this look like the inner product of two vectors? It does. What is the first vector? Grad f transpose, and what am I multiplying it by? Yeah, okay, we can. Grad x is not the correct notation over here. We'll just call it delta x, let us say. Okay. Okay. Now, to kind of nail this idea down in the case of multivariate, it's very easy for us to write a formula, but let's put it into practice. Okay, so let's take a numeric, example.